Welcome to this session about tensor fields and differential forms. The goal of this session is to further talk about the building blocks for doing calculus on manifolds. In this session, we will more focus on intuition and examples, but also give some definitions. First, we will look at the example of the tangent spaces on the two-sphere. We will then try to paint an intuitive picture for differential one-forms. Once we have an intuition for one-forms, we will look at the gradient of a function which is an example of a one-form field. Then we will use our understanding of vectors and one-forms to define tensors. And lastly, we will show the example of a specific tensor field, the metric tensor, which is the defining structure of Riemannian manifolds. So let's start with a short recap of tangent vector spaces and the specific example of the two-sphere. So let's look at the example of the two-sphere. We have already said that we need multiple charts to cover the sphere. So what do we exactly mean? Basically, you can have different choices of charts, but we'll show here an example. So let's look here at the 6 different charts that together cover the sphere. I can show them basically by exploding them here, and then we can have a look of them. So these charts do overlap. When we put them back together, then we can see that together they form the sphere. On each of these charts, we have our coordinate functions defined. Here we see the first coordinate function and the second coordinate function. Let's put that back together on the sphere. Let's look again at the first coordinate function. And now we will visualize the coordinate functions as isolines. Similarly, we can look at these isolines for the second coordinate function, and we can look at the set of isolines together. Let us once more look at how this looks in the charts. So here we can see that these are perfectly straight lines on the R2 plane, or a subset of the R2 plane for each chart. Going back to the sphere, these curves of course are not straight lines anymore. At each point of the sphere, a tangent plane is attached. Let me move the tangent plane around here. The tangent plane here is shown in blue with the 2 basis vectors that form the basis for the tangent space. We can compute these basis vectors as tangents to the coordinate curves. So you can see that the tangent vectors, the basis tangent vectors here, nicely align always with the curves on the sphere. It's important to note once more that the tangent vector spaces are uniquely defined at each point on the manifold. This definition is purely geometrical and completely independent of the choice of coordinates. However, once we choose charts and coordinate systems, there is a naturally induced basis of the tangent vector space at each point on the manifold. In practice, this is very relevant for visualization of flow data on Riemannian manifolds. For instance, in climate science and oceanography, the flow data that we deal with is always given with respect to specific charts and coordinate systems. Typically, the choice of chart and coordinates is implicitly given by a certain file format or convention. This convention induced a basis for all tangent vector spaces. The explicitly stored velocity data that we work with is given simply as 2 numbers at each data point. These 2 numbers are the 2 components of a vector with respect to the chart-induced basis. Before we start looking at differential forms and tensors, let me make a quick remark about coordinates. The laws of physics have to work independently of the choice of coordinates. That is part of the very definition of a physical law. We want to have equations that do not depend on a specific choice of coordinates. So it makes sense to deal with mathematical objects that are coordinate-free, that have meaning without coordinates. Tangent vectors, differential forms, and tensors are objects of this class. Therefore, it makes sense to attempt to build a strong intuition for them. Later, we can see coordinate-free equations just as recipes that tell us how to compute things with a specific choice of coordinates. The mathematical framework that allows us to do this is called differential geometry. Manifolds, charts, and tangent vectors are probably already familiar to most people in computer graphics. But now we will look at two more equally important coordinate-free objects that might be less familiar. Let's start with differential one-forms, and later we will have a look at tensors. Differential forms are extremely useful in practice. They allow us to define and compute integration of functions over curves, surfaces, and volumes. They allow us to evaluate a directional derivative of a function on the manifold. They are used in all these computational applications, and they do all of this in a coordinate-independent way. It is obvious that they are extremely important, so we will now spend a few minutes to try to visualize them and to build some intuition for them. We have already seen how we can construct basis vectors for all the tangent spaces on the manifold. Now let me see how we can, from these basis vectors, also construct a basis for the one-forms. Let's pick one tangent space here with its associated basis vectors. And now let's try to visualize the one-forms that are associated with this particular space. One-forms take a vector as input and generate a scalar as output. Here we see a visualization of a particular one-form. The lines are again isolines that visualize which vectors are mapped to the same value. So each vector pointing to the same line will be mapped to the same scalar value. Shown in red are positive values and in blue are negative values. Here in this example, the blue vector points to the fifth line. Since these isolines are spaced with 0.2, we can conclude that the one form of this particular blue vector here results in 1. This particular one form here is the first one form basis. If we look at the second one form basis here, we can see that the second basis vector points to the one isoline of this one form, which means it results in 1. So again, the one form takes a vector and evaluates to a scalar number. Here we have shown the two basis vectors of the tangent space and the two basis one forms of the one form space. We can construct any one form by a linear combination of the one form basis. So let me change here the parameters a and b a bit to let you see how different one forms would look in this one form space. Again, all of them are just linear combinations. We can see when the values get higher, then the isolines move closer together. Let me do one more example for a particular one form and a vector. So let's look at the second basis vector here in purple and at this one form. We can see that the second basis vector almost exactly points to the 0.2 isoline, so the one form would evaluate to 0.2. Now, of course, we can not only evaluate one forms for the given basis vectors, but for any vector in this tangent vector space. So let's have a look at a certain vector. Here, let's look at the yellow vector, which is just a linear combination of the basis vectors. And if I choose this particular vector here with this particular one form, this would evaluate to 0.8 because it is pointing to the fourth isoline of the one form. Let us look at a different tangent space. Again, the tangent spaces are constructed with the basis vectors, which follow from the coordinate functions. So here we can see now the two basis vectors and the linear combination of them, which is the yellow vector. If we want to look at the basis one form, the first one, that's the one form with the components 1 and 0, it would look like this. Again, the first basis vector is pointing to the 1 isoline. If we want to look at the second basis of the one form, it would look like this. Our yellow vector now would evaluate to 0.4. So these are just examples how we can imagine one-forms and how they are evaluated in a particular tangent vector space and one-form space attached to one point of the manifold. Now, this is not particularly useful because we haven't said anything how such a one-form would be defined. We just know how we can evaluate for now. We have seen that one-forms live in the one-form space at one particular point on a manifold. A one-form takes a vector as input and outputs a scalar. From our choice of coordinates, we constructed a basis for the tangent vectors and the dual basis of the one-forms. We have seen that we can visualize a particular one-form as a set of equidistant isolines. They are equidistant because the space they live in is a linear space. If we evaluate a one-form for a given vector, we can kind of read off the resulting value from the stack of isolines. It is interesting to note that for a given one-form, all vectors that point to the same isoline will evaluate to the same value. This provides us with a geometric picture, and we can build an intuition for how one-forms work. Now that we know how a given one-form is evaluated at one point of the manifold, we can define a one-form field. Let us look at a specific example of a one-form field, the gradient of a function. The gradient of a function is defined as a differential one-form field. Because the gradient of a function is a one-form, it must take a vector as input and produce a scalar. We are given a smooth scalar function f on the whole manifold. The gradient of that function at any point of the manifold is defined as the linear combination of the basis one-forms with the partial derivatives of the function. The meaning of this particular one-form is the directional derivative of the function f in the direction of any vector. Let us look at a specific example of the gradient of a function on the sphere. We can take as an input a function that is defined anywhere on the manifold. And we can compute the gradient of this function. The gradient is a one-form. It takes a vector at any point and evaluates to a scalar. So here's a visualization of the gradient one-form of this particular function. If I move around, you can see that the one-form isolines are always tangential to the isolines of the function. Let's look at a particular vector and see what the one-form would evaluate to. The vector points in the direction of the gradient, so it would evaluate in a high value. If we look at the same one-form at a different point on the manifold, we can see that our yellow vector would evaluate to 0. We have seen how tangent vectors and one-forms form vector spaces at each point of the manifold. Next, we will use them to define tensors. Tensors are defined pointwise on the manifold. They are maps that take one-forms and tangent vectors as input and produce a scalar as output. Because they are based on one-forms and vectors, they are also coordinate independent and therefore play an immensely important role in physics. They can be classified by their order, which is the number of input arguments. A tensor of order nm takes n one-form arguments and m vector arguments. The number of all arguments together is the total order of the tensor. There's a lot more to be said about tensors. Unfortunately, we will not have time for that today. So I will focus on one very specific example of a tensor field that will hopefully help us to get some intuition. In fact, we have already seen a simple tensor field. The gradient of a function that we just saw is a one-form that accepts one vector argument and gives us a scalar. As such, it is by definition a 0-1 tensor. However, now we will look at another example that is equally important. The metric tensor is the defining structure of Riemannian manifolds. For instance, let us have a look at these three examples of topologically equivalent two spheres. Only the one in the middle has the metric tensor defined such that it coincides with our familiar geometrical sphere. So the metric tensor is the structure that defines the geometry of a manifold. It is a specific 0-2 tensor field which is often simply called the metric. A 0-2 tensor takes two vectors as input and produces one scalar value. The metric tensor has the role of the inner product. It evaluates to the product of the length of both input vectors multiplied by the cosine of the angle between them. This allows us to measure length and angles between vectors. We can calculate the squared length of a vector by using it in both slots of the metric tensor. Likewise, we can calculate the cosine of the angle between two vectors by evaluating the metric tensor and then dividing through the length of the two vectors. The metric tensor takes two vectors as input and computes the inner product of these vectors. To visualize the evaluation of the metric, we will do a small trick. When we take one of our vectors and put them in one of the open slots of the metric tensors, we are left with a new tensor that has only one more slot for a vector open. Such a 0-1 tensor is by definition a one-form. Since we already know how to evaluate a one-form, we can use this trick to visualize the evaluation of the metric tensor. Let us take the first vector and fill it into the first slot of the metric, which converts it into a one-form. The one form we see here happens to be perpendicular to the yellow vector in the tangent plane. This is not a coincidence, but it follows from the specific choice of our metric here. However, it is important to note that this does not hold in general. Let's look at a few examples. So when we keep the yellow vector fixed and the associated one form fixed, and we change the other vector, we can immediately read off the result of the metric. So now we can see if this coincides with our intuition of an inner product. For instance, if I make the second vector equal to the first vector such that they coincide, then we can see that basically we can read off just the yellow vector, and that would be the squared length of this vector. If I changed the first vector, then the associated one form would change too. Let's look at another example. So here we see the first vector and its associated one form, and the second vector would read off from the lines of the one form. If I try to find a vector that lies on the zero line here, then this would coincide with our intuition for the cosine of the angle between them. It evaluates to 0. As I already said, we have used a small trick here to visualize the evaluation of the metric tensor. We have converted one of the vectors into a one form by filling one of the slots of the metric. In fact, this is more than a trick. The metric is precisely defined as the map that maps vectors to one forms, and the inverse of the metric maps one forms to vectors. We will make use of this property later in the tutorial. Obviously, there's a lot more to be said about tensors and differential forms, but I hope I could at least provide you with a little more intuition. Thank you for your attention.